Hello, the goal of this session is to introduce basic concepts and methodology of machine learning from a historical perspective. Um, for this, I want to start with the story of Tycho Brahe and Kepler. Tycho was a well-known person in the 16th century, and he was a very good observer. He collected data for the positions of planets, sun, and moon, and all these tables are called Alphonsine tables. He spent his life for this. Then he met Kepler at a meeting in Prague, and he invited Kepler as his assistant. Kepler accepted it. Then they spent 1 year together. We now know Kepler among other famous works of him, but mostly by the laws of planetary motion. It is not that crucial at this stage if you know this laws of planetary motion, but very briefly, they describe the basic principles. There are three of them, such as the shape of the orbits and so on. Here, the point is that what Kepler did was to make sense of the data in Tycho's tables, and remember that Tycho spent his life, Tycho Brahe spent his life to create those tables by observing each and every night the positions of they're called heavenly bodies on the sky. And Tycho never learned about that. I mean, this happened, this invention of the laws of planetary motion happened after 7 years after Tycho's death. And the point here, from our perspective of this lecture, is that these laws of planetary motion, were able to predict the data in the tables. So if Tycho Brahe did know about these tables, it would not be necessary to collect data. But it is an interesting story in that sense. I use the terms making sense of data and predicting the data, and the backbone of all these ideas is to identify regularities in data. And we know this field in the past several decades as pattern recognition. Here the point is that the pattern recognizer was Kepler's mind. And in incoming slides, I will be explaining this concept of learning, machine learning, by giving examples from various domains. One of well-known examples is to recognize handwritten digits, which is quite a straightforward task for humans visually. I mean, once you see these figures, you immediately recognize them as digits, 0, 1, and so on. And here, from a technical perspective, what's happening is that it was a difficult problem for computers to solve for many years. This is because of the representation of these figures in numbers. So you have to represent these numbers as vectors, and in this context, what I mean by a vector is a set of numbers that represent the intensity values, color intensity values here for each pixel. So each of those squares in this example is 28 by 28 pixels, which means that they can be represented by a vector of 784 real numbers. And as I said, each number represents the intensity value of each pixel. To clarify this, for example, suppose that you are starting at top left, which is a white cell, white pixel, and let's say white is represented by 0 and 0 and goes like 0, 0, 0. If you go to the right, then you continue with the next line, then you come across with a colored pixel, and you can represent it with a larger number. So I will show some examples of that in a minute. Here the point is that, can we identify a set of rules, as Kepler did in planetary motion story, which are able to identify these figures as numbers? So this is not quite a straightforward task. Actually, it is indeed impossible for practical reasons. Then in such cases, the alternative was in 1990s. This started. The idea is much older. I mean, it goes back to 1950s. There is a researcher, Samuel, and in 1959 he wrote an article about machine learning. But then the implementations appeared in 1990s. So this is the point. And what we mean by machine learning model is very important in this concept. The model is a function, and let it be a linear function. To give an example, it of course doesn't have to be a linear function, but here the point is that whatever function it is, it has to have parameters. And in this context, if it is a linear function, the parameters are a and b. So the function is the y function, and the goal of the model is to find appropriate values for model parameters in such a way that this model is able to recognize these figures as digits. We call this parameter tuning. So this is for parameter tuning. What is needed is a training set. I will clarify what I mean by a training set in a minute. Eventually, what we want to do is that we want to train a model. We want to train a machine learning model in such a way that this function eventually is able to discriminate between these figures, or it is able to recognize these figures as representation of digits. Here is an example. Let's say that we have this figure, and you immediately recognize this figure as the digit 2, of course, as humans, but to be able to represent this for a computer, we have to develop a vector. Let's start with the top left corner, and let's assume that the white color is represented by 0. Then if you read it like this, 0, 0, 0, each 0 in this context means each a pixel side by side. I assume that you start from top left and read this figure from the left to the right. Then after a certain stage you come across a blue color, and it is let's also assume that there are blue pixels with different color intensities, and these may be represented. If you assume that your maximum range is 256, then you will have numbers like 220, 236, and so on. And this vector eventually will consist of more than 700 numbers, which represent pixel intensity values. And we also say that this vector represents digit 2. Here digit 2 is our target value. What I do is that I give this to the model. I say that, look, this is the vector, and this is the target value 2. Here is another vector, and this is the target value 8. And another vector, another image, and the vector that represents the image, and here is the target value 5. And maybe you give another picture of the digit 2, then you say that this is also 2, here is another 8, here is 4, here is another 4, here is 9. Then you give all these figures, vectors, and their corresponding target values, and as we feed all this information to the model, we train it. Here, training means parameter tuning. And at this stage, let's assume that the specific model is not that important. So there may be linear and non-linear and other models. But the point is that what we do up to this point is called training. So this is the learning phase. First phase is called the training phase. And suppose that we finish this training. So we fed all the training data to the model, and we now have the model, machine learning model, which is simply a function with parameters tuned. And then we are going to test it. In the test phase, we are going to give a new figure to the model, which has not been represented to that before in the training phase. This is important because otherwise it would be only a memory retrieval problem, but we don't mean that. We want that this model is able to recognize this new figure as digit. Then it will be a prediction. So the model is expected to say that here this figure is the number 3, let's say. And if this model is able to do it for all the digits, which are represented by different digit figures, handwritten digits, then we say that, okay, this model has good generalization. So to sum up until this point, what I said is that we have the training phase, which is the first phase, then the test phase, then we would like our model to have good generalization so that it becomes successful with novel examples. It is called supervised learning. This idea, this core idea, has been applied to many different problems. So here is another example. It's automatic recognition of faces. And suppose that I present you this figure and you immediately recognize this face. And in the background, what this figure has is that it is approximately composed of more than 3 million, approximately 4 million pixels. So very small dots, each having a different color intensity value. So this figure can be represented by this very long vector to the computer in the same way as the digit figures are represented in terms of vectors. So this may be a login interface if you like, but whatever interface it is used, it will be too many data points for many systems. Of course, computing power is getting larger and larger, and it may be a small problem for novel devices, but there are many contexts in which it is not necessary that we should process all the data as raw data and feed it as it is into the model. So for this, in most cases, we use a pre-processing step, and pre-processing means kind of abstraction from raw input data into another set of variables in a predefined space. So in this context, in the face recognition context, this may be represented. um, I will skip some of those points which are not very crucial, but very briefly I will make certain assumptions about the sizes of these vectors and sizes of these picture segments, and this problem will be much more difficult in a video stream than a static image, but one good example of this, one of those kind of optimization pre-processing stages has been an algorithm proposed 15 years ago. And it is a good example because this is what you see when you take a photo with a digital camera. You may have noticed that it is able to catch faces automatically by drawing a green square or rectangle on top of the faces. What it is doing is that it is identifying certain sub-region features so that it is able to reduce the requirement for processing power. And so here is an example. If you take a picture of this with a digital camera, it will be able to separate this face region from the rest of the figure by making certain assumptions assumptions that were introduced by those algorithms. Okay, so here, when we go back to the general problem, suppose that I am designing a login interface and let it be a face recognition interface. So the user will provide faces each and every time he tries to log into the system. He will provide faces with different angles, different light conditions, maybe with glasses, maybe with different color style, and I expect my machine learning model to recognize this person and to separate this person from other people who are going to use this computer. So this is the task, and here the point is that again let this first set be my training set. Then in the second set below, I assume that I will give a novel example, novel mugshot, and I expect my system that the third um, shot would be recognized by the machine learning model. And um, so here again, the point is, the first is the training example, the second one is the test set. It is important to very well understand the concept, this difference between the training set and the test set. So the members of the test set cannot be the members included in the training set, otherwise it would be a sole memory retrieval problem. But we would like learning, we don't want memory retrieval. And this can be extended to many different domains. One of them is one of popular domains that machine learning algorithms have been used is spam filtering. And to start, we should first consider the challenges if we attempt to identify a set of rules for spam filtering, as Kepler did. I mean, Kepler invented the rules for planetary motions, but these are different domains. Spam email is a different story. It is not easy to come up with a set of rules for a set of reasons, such as their dynamicity and their higher number of these terms. Also, there are problems with false negatives. So, for all these reasons, it is impossible to find an appropriate spam trigger term set, and for that reason, for spam filtering, machine learning approaches are adopted. So there is no rule-based algorithm, but we expect that there is an input, which is an email message, a piece of text, and we would expect our model to predict this text as a spam message or not spam message. Here, one important point is that as a user, when you read your emails, you will possibly have a spam box folder. And in this spam box folder, actually it is the output of classification. I mean, the email provider will tell you that, okay, these are your spam emails, and if this is not a spam email, please mark it as not spam. What you are doing here is supervised learning. So you train the model actually. So as you provide this data to these models, they will get better and better because they will learn from its own users to classify between spam messages and not spam emails by means of supervised learning. There are many different applications of this idea. One domain of application which is popular nowadays is called recognition of emotion from facial expressions. Actually, here, if you train your system by assuming that there are specific types of emotions, which is a challenge by itself, then this system can be trained. It may learn how to classify different faces and how to report the weights of these emotions by presenting a kind of a mixture of emotions in given faces. Here, the scientific problem is a bit different than that. I mean, the machine learning problem is the engineering problem. But scientifically, the research question may be, is it really that the emotions can be categorized into, let's say, 8 different classes? So this is the scientific problem. And recent research in emotion recognition says that it is not that straightforward. I mean, most of this literature come from a book by Ekman, which was published in 1980s, and he gave a broad classification of emotions. So if you make an assumption that, okay, that is fine with me, it is okay. The rest is the engineering problem. But if you ask, what if I give only 2 emotions, and what if I train my model in such a way that it is able to classify only 2 types of emotions, then it is a scientifically wrong, incorrect assumption, but in terms of its engineering, that is fine for the model. It will accomplish its task anyway. So I don't say that it will do it very accurately. It is another problem. But here, the point is that don't lose this scientific point. I mean, you need to become a researcher. You have to conduct research on types of emotions to be able to design a good classifier based on scientific findings. So don't confuse this engineering stuff with scientific stuff. Okay, so here what I said so far has been supervised learning, and there are historical roots of this supervised learning methodology. And if you go to the literature of 1990s, you come across methods called concept learning and decision trees, and we don't talk about them much nowadays, but don't be simply misled that by assuming that they are useless, because there are certain systems like live systems, let's say in cybersecurity, in intrusion detection systems, or in systems that would have limited computational power. You may prefer using these simpler methodologies due to their speed. So it is not uh, only the deep learning story, but you may also need all these different algorithms. You may have to employ them for high performance. And we don't have time to proceed with details here, but here the point is that if you put something on top of this concept learning and decision tree idea, you would come across regression. Regression basically means that you define your output as a function of the input. Suppose that you have 7 data points as shown here. It is a relationship between a variable and a function. And you may say that, okay, this looks like maybe a second order polynomial or a linear function. But when you say that it is a 6-degree polynomial, it would give an exact fit, but you would become unhappy of that. This is called the overfitting problem. So when you go into the details of machine learning design and algorithm, use of those algorithms, you will come across this as a problem, overfitting problem. You have to use so-called regularization to overcome these problems. This is the beyond the scope of this lecture, but it is important that you become aware of these issues too. And if you develop this regression further into logistics regression, you come across the concept of classification. Very basically, the idea is that suppose that you have a set of variables in a space, and for the purpose of demonstration, it is a two-dimensional space here, mileage of cars and their engine power, and you may want to classify these data into two parts by identifying a linear boundary function which separates this space into two parts. So this can be done by artificial neural networks and support vector machines. So if you want to deal with classification problems, you will come across with these methodologies. Very basically, an artificial neural network is a mapping from the input to an output. This output may be a single cell which has binary values 1 and 0, or it may be multiple cells too, and this mapping is identified by kind of normalization of inputs in terms of their weights, I mean influence on top of the output. This is of course very simplified representations. You should learn them in detail if you are going to become a researcher on machine learning. So this is just the goal of this lecture is just to introduce the basics of the methodology and concepts. And there are other methods. So far we talked about supervised learning methodology. Unsupervised learning basically means that you give data to computer and you say that, okay, cluster this for me, identify classes. And it is better to explain this concept by means of an example. Suppose that you have coins, and these coins have specific size and mass, and they are worn by time. I mean, as you use coins, they lose some of their mass, their size changes a bit. So here the point is that you may want your computer to cluster a set of coins into 4 different groups if you know that you already have 4 different groups, like 1 cent, 5 cents, 10 cents, 25 cents, let's say. And here the issue is this. If you say that I have 3 sets, then the computer will classify or cluster, to tell it better, cluster it into 3 groups. So There are other methods, but very briefly, it is my goal is to inform you about the challenges as well as the methodologies. So if you continue searching in machine learning methodologies, different types, you come across the concept of Bayesian learning, which is based on probability estimates, and reinforcement learning. Reinforcement learning has been very popular in games and nowadays robotics too. And the idea is to give a score to successful attempts or unsuccessful attempts. So if you have a game score, which is based on winning a game or losing a game, then all the moves can be traced backwards to give whether positive or negative values to them. So this is very basic kind of reinforcement learning idea. It's based on maximizing the cumulative reward. So to sum up so far, I introduced some of machine learning methods, mostly supervised learning and partly unsupervised learning. I skipped some of them, and I introduced Bayesian learning and reinforcement learning. Of course, in our day, deep learning methodologies are popular. I mean, since 2012, even some researchers, they say that it doesn't worth to focus on previous methodologies in machine learning, but it is not quite a strong claim. I mean, these are deep learning methods are very successful. They are extremely successful, very powerful, high performance, super high accuracy. So they are wonderful for engineering purposes. They are of various types, and one of the architectural differences between other machine learning methodologies and deep learnings is the structure of the layers between inputs and outputs, which is again kind of mathematical functions. And but despite their very high accuracy, one challenge is that they are black boxes for us. I mean, it is not clear how a machine learning model makes a decision. This does not only apply to deep learning methodologies, but all artificial neural networks. Exceptions are decision trees and so on. Concept learning, these are very explicit. You can go into the details and you can understand how the model makes a decision. But in artificial neural networks and in deep learning methodologies, this is the challenge. So these are black box models. We don't know how they make decisions. Why are they important? Suppose that you are running a bank and you are going to give credit to a customer, and your model makes a decision about whether giving the credit or not. And here the challenge is that how this decision is made, it is not clear. So there are many cases as such. I may consider health diagnosis systems. It is the same problem here. If the decision turns out to be incorrect, then you have a problem because you don't know how the decision is made by the model, despite its huge success in accuracy and performance. So this is one of the big challenges of our time, and the proposed solution to that nowadays is called explainable artificial intelligence, explainable AI, and I hope in near future we will see how explainable AI will turn into a research topic by itself. Okay, good. Thank you very much for your patience. Okay, see you then.